we were talking about logistic regression, and we saw that you can think of, so the idea was, how do we fit logistic regression, right? And the idea is that to fit logistic regression, we can use the maximum likelihood idea. So you have some training data. It's coming from some joint, like a conditional distribution of y given x, and then we form the likelihood. And the likelihood is really the joint density when viewed as a function of theta. So it's in our case, usually, not always, we'll see. Your like observation, if they're IID from the model, then this joint distribution of y conditional on x's factorizes into these coordinates. Right, so it factorizes in this fashion. And for each one, in the case of logistic regression, we have an expression. So this is the probability of observing yi given xi. And in a logistic regression model, this is basically probability mass function. This is probability of y equal little y given x is equal little x. This can be written as or modeled as sigma of theta transpose x in logistic regression. And so if y is 1 is like that, if y is 0 is like the other, 1 minus this. And so the maximum likelihood estimator just tries to maximize this. And when you try to maximize this, we went through the argument that it's equivalent to minimizing the negative log likelihood. So negative log of this, or negative 1 over n log of likelihood. So 1 over n doesn't change the minimizer. So this, when you write it down, it would look like an empirical risk minimization with the negative log likelihood of a single sample being the loss. And so we went through the details of what this looks like for the logistic regression. So there's this compact form of writing the logistic regression probability mass function. You can rewrite it in terms of this loss that we defined. So binary cross entropy loss, which takes a label y and a probability and measures the loss. And we saw that in terms of this loss, basically the MLE in logistic regression is like yi and sigma theta transpose xi. So I'm calling g theta here. We apply this binary cross entropy loss to it. The alternative loss was the log loss. So there's another loss which we called log loss that sort of absorbs this. So there's a sigma here that it's always there, so I can absorb it into the loss and define a new loss. So this new loss is connected to the binary cross entropy via this. So log loss of y and z is the binary cross entropy loss of y and sigma z. And so this acts on a logit. And in that loss, this logistic regression problem looks like this, which is very simple. So you apply this log loss to y and theta transpose xi. It looks very much like linear regression, in which the loss is just the quadratic loss. So if this was quadratic loss, it would look like yi minus theta transpose xi squared. This is a more generic, like not the generic, but it's like a more fancy loss, but otherwise it is of the empirical ERM form, and we can just as easily solve it. This log loss is convex in Z, and I made a mistake of saying it's strongly convex. It's not strongly convex, it's strictly convex. There's like a small difference. So over the entire real line, it's not strongly convex. So a strong convexity would mean that it's something greater than would be bounded below uniform The strict convexity means the second derivative is positive. So the second derivative is positive, but you can verify that it just goes to 0 as v goes to infinity. So it's not strongly convex, and that's one of the issues that causes a lot of ishtic problems with optimization. Quadratic loss is strongly convex. So that was a mistake. So I probably mentioned somewhere that yeah, strongly convex is not right, strictly convex. So just make sure that you correct that in your understanding, strictly convex. So composition with a linear function preserves these properties. So this optimization problem of the cost function here is going to be strictly convex, and so we can solve it. In particular, gradient descent has one position to converge to. So there are no local minima, there's no saddle points. If it converges, it's going to converge to this, like a minimizer. Okay, sounds good. Questions? This was last time. So what I want to do today is sort of extend the idea to multi-class classification, and maybe to like a special example, which is we'll see like whether you want to go there or not. It's like a very simple language model, like the precursor to these chat GPT and stuff that's coming out. We'll see how far we can go, but once we talk about multi-class classification, multi-class generalization, the logistic regression, there's a little like one step to this bigram language model, which is a very simple language model. But we might talk about that during a time. If you understand that there's like a little step to GPT, and the rest is basically like having infinite amount of computational power and infinite amount of data to just throw at it and just tweak it to get what these guys got. And like there are some other like interesting components to it, but there's not like we're not far from like you're not far from understanding what is going on in GPT once you like understand that bigram language model. Okay, so before doing that, so today is like going to be multi-class version of this, but before doing that, I want to do a little side note here. So gradient descent with momentum. So what happens if we tried this in code in PyTorch, and if you try to solve this by gradient descent, it's going to work for simulated settings. But for example, if you try to run it on the real data, on the breast cancer data, you're going to see that it's going to converge very slowly. So you have to make the step size very small, and it takes forever to converge. So for this reason, usually people in practice, if you do like R package or this packages like scalar in like Python, they use more advanced, like higher order, like second order methods to solve logistic regression. Second order method would be Newton's method. So the gradient descent, if you remember what we did, gradient descent sort of minimizes a linear model, local linear model of the function. So you do Taylor expansion up to the first order and you try to minimize sort of that linear model, the tangent basically. Newton's method sort of fits a quadratic function, so minimizes a local quadratic model. The function, so the quadratic model touches the function, like it better approximate the functions close to the current point. And in order to do that, you have to write down the Taylor expansion up to the second order. Okay, so you get a quadratic term as a second order, but in multi-dimensional cases, that quadratic term requires you to compute the Hessian matrix, which is going to be like a D by D matrix. And there are some issues there. So, so you're not going to go there. It's like, optimization course is good to to go there. And they're like quasi Newton methods that try to approximate the Hessian without computing it and stuff like that. But this idea of gradient descent with momentum is very interesting because it's like a very tiny modification of gradient descent, but it does wonders in practice. I just want to tell you about that and show you what it does. Has anyone seen this before, gradient descent with momentum? Okay, what is it then? It seems like some people have seen it. The gradient descent, suppose I want to minimize if theta, theta in RD. So in gradient descent, what we do is like, we form these iterates, step size, gradient of f. So we move in the direction of the negative gradient. So this is the vanilla gradient descent. So what is the gradient descent with momentum?
They're like a variable step size.
That would be gradient descent with variable step size. If it's fixed step size, that would be variable step. It's not variable step gradient descent. It's a little bit more clever than that. Anyone else? So it's like a little bit of memory. So what you do is you keep a memory, like a short-term memory. So you form this sequence ZT, which I think, well, yeah, you use alpha probably. So, sorry, alpha here. So alpha times ZT plus 1. Yeah, theta, and then theta plus 1, theta minus gamma z t plus 1. So if this alpha, this is a number here, so this it's going to be, alpha is going to be in 0 to 1. So if this is 0, you can see that zt plus 1 is going to be the gradient. And then when I plug it in the second equation, I get just the gradient descent. Okay. But this alpha, if it's not 0, then it's going to bias me towards the previous value of the gradient. So you see like zt would be alpha zt minus 1 times the gradient of the previous step. So this keeps like a memory of the gradient step. If you've seen AR processes, it's like an AR process, like AR1 process. So at 0, let's say I can initialize it at 0. So take z0 would be 0. And so the first step contains the gradient. So z, for example, let's say z1, z0 is 0, z1 would be gradient of f at theta 0, right? And then I get theta 1 is theta 0 minus gamma z1, and then z2 would be z1, like alpha z1, plus gradient of f at what? At theta 1, right? And then theta 2 would be theta 1 minus gamma z2, right? So if you plug in z1 here, you see that would contain the gradient of the previous step. So I'm having like alpha times that plus the gradient at the current step. So I keep a little bit of like bias towards the gradient of the previous step. So if alpha is very large, I'm going to be more biased towards the previous step. So I'm not going to like change the gradient too fast. I'm going to keep some information of the gradient. And if you like expand it, you'd see like, because of this, you'd have like exponential memory. So you'd like have the residuals of all the past gradients, but the vase gets smaller as you move towards the past. So the past gradients get like multiplied by alpha to some power. The previous one would be alpha times this, but at the t step, the gradient, the 2 step before would be alpha squared times that smaller, alpha to the third and so on, because it's less than 1, alpha to some power, it's going to get really small. So it's going to quickly lose information. Like It's memory, but there is a bit of memory. You keep the gradient of the previous step a little bit. It seems like a very tiny modification. But I just wanted to show you what it does, which is very interesting. So any questions? Yeah.
What are the optimal values for alpha and beta?
Let's not go there. That's a very good question. In general, it's hard to answer that. Even the step size in gradient descent is it's not obvious. You see, like also in Howard problems, that there is like a maximum before you even diverge. Let's not worry about that too much at this point. Okay. There is a good answer to this if you're minimizing quadratic function. And I'm going to show you a web page that you can go through. And it has a demo actually, and it talks about what the alpha and gamma should be optimally when you're minimizing quadratic function. But in general, I don't have a good answer for that. And we can come back to it. Okay. It's a good question. Let me show you what it does. Any other questions? Questions? Yeah.
Like the stochastic gradient descent with momentum, or like atom optimizer, are those like the best ones to use?
Stochastic gradient descent is a variation of the gradient descent. We talked about that. And a stochastic gradient descent with momentum would be something like that. So that atom optimizer is using an idea like this plus some other idea, which is a combine. Yes, you can use that, but you might use it, but it uses some sort of an idea like this. Plus another innovation, which is which we may or may not so why momentum really works. So this shows like an optimal point. There's a starting point, and this is the gradient descent step size 0.2. Momentum is 0. Okay, so that beta is alpha in my notation. Alpha is really gamma. That's the step size. Okay, so now if you increase this, see what happens. Okay, it pushes it. This is the same amount of step size, but it just pushes your solution. So there is some oscillation, but it sort of also gets rid of the early oscillation. So you can see if I increase the step size, at some point this is going to diverge. Okay, but even with this large step size, this momentum sort of fixes that issue and it pushes this too. So the same number of step size, but it improves the convergence dramatically. So like you can like get very crazy with it. Okay, but yeah, you can see. Okay, let's see. This is where gradient descent doesn't work, right? So the step size causes divergence. Now if I increase the momentum, you can see it just fixes it. Even if with a crazy like step size, you can still achieve something. So you can improve that, you can increase your step size and also improve your convergence. It just dampens the oscillation as well. So this goes through a great deal of discussion and you probably can follow perfectly. And it does it for the quadratic case and like tries to understand what is going on and why it really works. It's a very good article. I'm going to post it and you can read it. I just want to show you why it really actually works in practice, and in practice you might not necessarily be using the gradient descent. So let's see it on our data. I'm going to show this, and get rid of this. Okay, so let's work out the. This was our like gradient descent last time. So this is the simple data that we generated. If you remember from like a logistic regression model with a Gaussian prior. So let me increase that. Okay. So that was the log loss. So we had the log loss, we minimized the log loss. And this gradient descent, this was our gradient descent. I like gave it the loss and then theta. And so this was what it did. So it's like a step size 1, 500. And this is the way that it like sort of converge. So if I now change it to this gradient descending momentum, I'm going to show you the code. The code is really simple. With the same step size, you can see we're going to go like move away like that, but you can come back. So it might not seem like a lot of improvement in this case, but I can like reduce the step size. You can see like we're still like pretty close, right? And see if I can increase this. 2 even I can increase. Oh, sorry, this is not affecting that. So let's say 50. Yeah, not 2, but I can like do 50 and 2 maybe. I think it's like overshot and then came back probably. So let's see. Yeah, maybe too much. But you can see the momentum is like this parameter they added here. So without it, it's like that. With it, at some point, it's going to improve. So so that's the code. So the only modification that we're making here is this sort of step. So instead of just adding the gradient, like taking the step in the direction of the gradient, you just keep these z, right? So z, I'm initializing it as 0. And then here, I'm just updating z by this momentum parameter, which is alpha in our case times z plus the gradient, and then apply the learning rates to z and then subtract from beta. So that's the gradient step, but gradient in terms of this latent z, not the gradient. That's the only modification. The rest is the same as our previous. So this was the gradient descent. This is the gradient descent momentum. Okay, now why this really works. Okay, this will show you this is the breast cancer data that you saw in your homework problems. Let me plot it. So that's the radius mean, that's the texture mean, and the 2 classes. Okay, so it looks like a logistic regression might be appropriate here, right? If you try to, let's then try to solve it. So I'm gonna like convert the training and training X and Y training to torch objects, and then what I'm doing here is concatenating a vector of 1, or like columns of 1 to the X train. So torch chat concatenates this to X train. Now, if you look at the shape of this, so it used to be like 398 by 2. Now it's like that. Let me show you what it looks like. So it has the columns of all ones because I want to have the intercept, right? So for real data, you really want the intercept. So there's going to be a theta here, multiply the 3 by 1. So the first coordinate would be corresponding to the intercept. So that's the loss function I'm defining, x train times theta, and then the loss is the same, okay? But theta is going to be 3-dimensional. Okay, so that's my initial theta. Okay, so let's do 0 here. So momentum 0, learning rate 0.4, 10,000 steps. And I'm doing gradient descent in momentum, but the momentum is 0. So that's really gradient descent. And then the output theta I'm going to stack into a tensor. So each row would be like one of these thetas. And then I'm plotting the loss, and I'm going to like show you the last loss. So this is gradient descent on that initialized at 0. So if you do this, so you can see that's the loss function. And let me show you 1,000. So like, so there is a lot of oscillation, you'll see, right? So there's a lot of oscillation, and it really has a hard time converging. Okay. Sorry, the momentum is, I wanted to increase this to like 500. So you see, there's a lot of that, and I'm gonna also plot the trajectory. So that's the trajectory in the theta space. Okay. So it does this, and you can see it's not gonna, like this oscillation is not gonna go away. And if you look at the theta, like this is the, each row is one of these thetas, this is in the end. So you can see there is this oscillation. So even at the end, if I show you, for example, this is what we're gonna do. So you can see the last 10 or so. So you can see that there's a flip between positive and negative, right? And like between these values. Now let's try, for example, increasing the step size. Maybe this, okay, step size is actually, if you decrease the step size, you'll see that like the oscillation goes away, right? But still, like the loss is like close to 0.4. It didn't go as low. Now, if I do the momentum here, 0.9, you'll see it goes down, and then I can increase the step size to 0.4. And you can see this very strange, interesting behavior. So it oscillates a little bit, but then like finds the correct thing and then just drops to this. So if you look at this plot, which I find very amusing, so it wanders around, but then shoots to the correct, roughly the correct thing. And the reason why this problem is hard is, you can now see the loss is not going to change much. So you can see, for example, it's like there is a tiny like improvement here. There's very like little, once you get close to this, you try to get to the minimum, like the part that's close to minimum is very flat. So it takes a very long time to get there. And this momentum sort of speeds things up. The parameters that you get are going to be, if you don't do like 10,000, for example, you still get a good loss. So for example, I do like even 1,000 here, I think the loss is going to be okay. Not completely, but you can see like the oscillation sort of dies down, like this slows down. But the parameter is going to be like still far off. So you can see the parameter is, it's like -11 something. So -18 is like, and then the rest is the correct sort of, not the correct, but it's like the optimal, what you do, like you'd get if you solve it using one of these fancier solvers. So okay, so that's the thing. And let me show you another step size. For example, you do, for example, if you start from -1, let's see what happens. So you can see a similar behavior. So like oscillates a bit and then shoots up to the correct location. That's the final result. And this is if you, let me show you. And it's too much stuff. Yeah, so this is what you get. So this is what you get as the decision boundaries. So if you plot the decision boundaries that you get for is it visible? So this is the classifier answer. The decision boundaries are linear, right? So the decision boundary is linear, it's somewhere here. So these are the level sets of the decision rules. This is the level sets of that sigma theta transpose X. So it finds the correct sort of location, sort of, right? So this is the boundary. So here, like everything is like one, here is everything is zero, and between things are murky, sort of. Not everything. Okay, and then I want to show you the solution that you get out of the usually scalar, like they have logistic regression. So if you do it, you get they do it using like fancier solvers, like causing Newton, you get negative 18.9. Here is 1.067.16. Our solution that we got out of that momentum is this, like negative 18, 1.05, and instead of 16, we got that. It's pretty accurate. And if you do it in R, you get a different answer, actually. I encourage you to do like GLM in R, and you get slightly different parameters. So figuring out the actual parameters is hard here because the loss is very flat. If you move a little bit of, like a tiny bit of, like around the optimal, the loss doesn't change. So the parameters are not very necessarily accurate, or you don't need them to be accurate, but the decision boundary is going to be accurate, sort of not change. So let's try, for example, if I do, what did I do? Okay, so let's do 1,000. So you can see the loss is increased by 0.29. And let's see. So now the value, for example, is negative 10, so on. Let me try to plot. So you can see the decision boundary doesn't change much. Change a little bit, change it, not too much. So even if you don't get the right theta, the sigma theta transpose X might still be good. So for prediction, you don't necessarily need the accurate theta. But if you really want the minimizer, in this case, you can figure it out, but you have to run gradient descent longer, a lot longer. And in this case, if you do 10,000 with this momentum, you're going to recover. If you don't do the momentum, it's going to be problematic. Okay, so this is a real world example of how you can like improve the gradient descent, and this is really used in practice, this idea. Plus another idea that would be that Adam optimizer that you mentioned. Okay, questions? It's a little bit fast, but I just wanted you to see in practice. If you try, it's very instructive to try to do gradient descent on this. I'll try to post this and you can play with it. And there are a couple of points that first, it's hard to minimize it. The loss function, I can't plot the contours of the loss because it's three-dimensional. The function is three-dimensional, like from R3 to R. But by looking at where it converges, you can see if you don't run it too long, you're not going to get to like the negative 18 or something. This is like the minimum. So you're going to stay away from that point. But in terms of the loss, things are not that bad. So if you play with this, you'd get a better understanding of the logistic regression. So any questions? And then you can also calculate the accuracy. In this case, accuracy would be, so what I'm doing here is, let's call this the model. So you can, once we recover, that's the last theta. Okay, so the last 10 step probe. This is going to take the last probe. When you do, like, this is a tensor. So a little bit of PyTorch. So this is a tensor of shape 1001 and 3. So I took 1,000 step, and the first one was the initialization. So if you want to look at, so you have a tensor, we can index it like this. So I can say 0, and this is going to take this first row, the 0 index, and all the other columns. So that would give you, that's my initialization. That's how I initialize. But you don't really need the second one. So if you do something like that, it's going to pick the first row. If it's like a multi-dimensional tensor, if you just index it by 1, it's just going to pick the like index through the first dimension and then outputs the rest. Like keeps the other dimension. So I can say, for example, and the -1 would be the last. So I can say -1 like that. That would be the last row, or I can just say -1. That would still be the last row. Okay, so the last row would be my last estimate. Okay, so and then I'm setting it to theta hat, and then I define this function. There's this decorator here at torch.nograd. So this makes like tells PyTorch to don't compute gradients in this function, so that you don't run into issues because we don't need the gradients here. So I'm just gonna do the calculation, which is torch.sigmoid. That's the sigmoid function. X, this is vector matrix multiplication, right? So remember, this is a vector, 3-dimensional vector. X is, I'm going to assume that whatever X I give, it's like n by 3. The rows are going to be my test points, and 3 is the dimension. So X is going to be, yeah, n by d and theta. I'm amazed by what this does. So it knows that. So n by d and then theta is d-dimensional. Okay, that's your language model there. When I apply it, for example, to the training data, it's just going to calculate the y hat, and then I'm going to compare the y hat to 0.5. It's better to call this p hat because that's really probability of that's like sigma theta hat transpose x. That's the probability compared to 1/2. That's my decision rule. It's like the estimate of the Bayes rule. And then I compare it with y, turn it into a float. It's going to be a binary, and then the mean would give me the like accuracy. How many are correct, and then the item takes, it's just a scalar tensor, so it takes it out. So the accuracy turns out to be 0.89. Okay. Questions? Yeah, and this one I have to clean up, but this just plots that decision function. So you evaluate this at different x's and you plot the contours, and this gives you the contours. So that's where the boundary is. Maybe 0.5 is somewhere here. Questions? So that's logistic regression realistically, and we solved it ourselves with just a little bit of help from PyTorch to calculate the gradient. The only thing that we used here that we did not do ourselves is this backward function which calculates the gradient. Otherwise, you hopefully now know like the inner workings of logistic regression, at least one approach, gradient descent with momentum. If you want, you can use that Atom optimizer and compare. Maybe we'll do this at some point or as an exercise and see how well you converge relative to that. So extension to multi-class classification. So logistic regression was probability of y given 1 is equal to x is like sigma theta transpose x. So now suppose, so binary classification is like that. Suppose y is in 0, 1 up to c minus 1. So there's C classes. So if C is equal to 2, that would be binary 0, 2, 0, 1. But in general, I have a multi-class problem. So how can I extend this idea? So how do we extend? How can we extend the logistic regression idea? Any idea how to do this?
One versus one.
Okay, so yeah, you can, one way to do it is to say, I can try to treat this as a bunch of like sequence of binary classifications. I can try to classify whether y is 0 or not, so any other one. So that will be one binary classifier. And then I'll try to do this versus the other one. So that's another classifier. And then like this versus the others. One bit of issue with this is that they might give you conflicting results, right? So I could say, for example, this might say this is 0. And when you try to do like 0 versus non-zero, the classifier says this is a class 0. And when you try to do 1 versus the other, it says it's class 1. Now you have to decide whether you're 0 or 1. One way is to take like kind of majority vote in a sense, right? So you run all these one versus the others, right? And then try to aggregate their decisions. So if all of them like are consistent, then fine. Otherwise, you have to somehow find a way to do it. There is a better way to do this, which you can directly just directly model the problem instead of trying to reduce it to binary classification. So to think about it, the thing is we can just model as easily this probability as y varies. I'm going to use this notation, C star. So that's going to be my notation for this set. So I'm going to call this set C star. So this is very common. This bracket C is the notation for 1 to up to C. This is not a standard notation, but I'm going to use it. It helps with zero indexing, similar to the above. But so for any little y in this class of labels, I just have to like specify a parametric form. And so let's think about what so what logistic regression does, so if C is 2, so what you really do is you're saying, I have the probability that y is equal to 0, like 1, is sigma of theta transpose x. If it's not, it's going to be 1 minus sigma transpose x. So I did not need to specify this because this has to be 1 minus the other one. So the reason why logistic regression this specifies probably y equal to 1 is because the other one is needed. Once you specify when the other one is specified. Here, we need to specify at least, if there's C labels, we need C minus 1 probabilities because the last one is going to be the sum of them. So I need something which is for C minus 1 dimensional. And the natural thing that you can do is that you can come up with like a function, which I'm going to write as S later. So this takes like theta. Okay, so let's see how I should do this. Okay, so let's do this. Not S. So I'm just going to have a parametric family here, G theta of X and Y. So G theta would be taking RD, that's the dimension of the features, and it maps it to R to the C. Okay, so if I have a function like this, parameterized by some parameter, okay, then I apply it, and then I take the Y coordinate. So G theta of X really is G, let's say 0 of X, G1 of X up to GC minus 1 of X. And what this operation is doing, so G theta of X, Y is basically like a simple way of saying, yeah, okay, so I have to put a theta somewhere. Yeah, this is really g theta, let's say, of x1. I'm gonna have to do it like this because there's a theta there. But these are just functions, like coordinates of the functions. 0, 1, up to c minus 1. And the white one is just, I'm gonna, if the label is 1, I'm gonna go and pick the white one, or like first one, second one. That would be just the probability of observing that label. So the only thing that I need to do is just come up with a parametric function to generalize the logistic regression that has this form. So maps RD to RC. These are probabilities of observing each of those labels for that value of X. And the only thing that I need to impose is that we need that summation of these g thetas as, let's say j, call it j. J goes from 0 to c minus 1. This has to sum to 1, and each one has to be non-negative, so that this is a well-defined probability. Okay. So if I have that, then I have a general parametric model. I can, if it's differentiable, I can try to write down the maximum likelihood and then try to solve the problem. Okay. So far, so good. This is very general. If I want to do logistic regression, this is sort of simplified. So if you think about logistic regression, it's just like that. So logistic regression would be, so for this, for c equal to 2, it's an example of this where g theta of x is just sigma theta transpose x and 1 minus sigma theta transpose x. So if you think about that, I can, if I write probability of y equal y, when x is equal to x, is g theta of x. The y coordinate, if y is, this is the 0th coordinate, 0th index. And this is the first index. So the 0 would pick this, 1 would pick this. So that's a special case. So I just have to figure out a function like that. And an easier way to do this is, instead of, because this has to satisfy constraints. It's hard to come up with functions like this. What I'm going to do is I'm going to assume that this is actually like there's this object called Softmax operator times another function here, f theta of x. So this Softmax takes a vector in R. So this f theta is in R d to RC again. And this softmax is another operator from RC to RC. So this takes any vector. So softmax of U takes any vector and produces. So this is a vector whose jth element would be e to the uj, and then summation e to the like u. Let's call this j prime, or like okay, ui, I from 0 to c minus 1. So it's just a fixed function, and it has this form. So you put in one vector if you want. It's just s of u0, u1 up to uc minus 1. It takes it and it outputs like the summation I from 1 to c minus 1 e to the ui, and then eu0, eu1 to eu c minus 1. So it does something like that, right? So why this is interesting, because this function takes anything in RC, and what happens to the output is actually, the output is always going to be in 0 to 1, and it's going to sum to 1. So if you look at the output of this, because of exponentials, this is always going to be non-negative, and it's also going to be, when I sum the coordinates, the summation would be just this summation here. So the summation is going to be 1. So what happens is just we always have SUJ, j from 0 to c minus 1 is going to be 1, and SU j is going to be non-negative. So this has the property that it produces a probability vector from any vector that you give it. So this simplifies my life because then this function can be general, so it can output real valued numbers. So it's very similar. So this is like an extension of the sigmoid function. So remember, in the sigmoid function, the reason why we needed this is because we needed probabilities here. So I wanted really a linear model, theta transpose x, but I couldn't just say that the probability is equal to theta transpose x because theta transpose x is real value. It can take like negative values, it can be bigger than 1. But we had this nice sigmoid function. The sigmoid function here is it maps real values to 0 to 1. This S function is like the multivariate analog of it. It takes a vector in R to the C and outputs a probability vector C-dimensional. Okay, so that helps me. Just now I can just model the argument of this. So this can be anything. And I'm writing it general, but if you assume, so this is Softmax function. Softmax. So we can now easily model f theta of x, because this maps something from RD to RC. If I want particular, if we want to model f theta of x as a linear function, we can, because the argument of the softmax can take any values. So how can I make f theta be linear? What is a general linear function from RD to RC? How you define like a vector value of your function, linear function? Linear math, linear regression. So x is like, I'm going to give you x. This is an RD. I want to map it to f theta of x, which is in RC, and what I want this map to be linear in x. What it would look like. Or what would it look like? What would it look like if this was univariate? If theta was scalar values? So I give you x1, x2. I want to map it to real. So a function of x1 and x2, which is real, like a number, but it's a linear function in x1 and x2. What is the general form for it? Add them together, that's a valid linear function. What is the most general form? Ax plus bx2, right? And a and b can be anything, right? So how about like if I had 3 elements? What is the general linear function from R3 to R? Yes, and then I would say that theta would be like A, B, C. Okay, the parameters are A, B, C. So it's like parameterized by 3 parameters. A general linear function from R3 to R has to look like this. I can call it like theta 1, theta 2, theta 3. So a linear function is really like that. So now imagine if this was from R3 to R2. So I have x1, x2, x3. I want a linear function from R3 to R2. What would it look like? Maybe I'm going to write it like this. So it takes these. So this one is like that as well. So this is that vector x. It has 2 coordinates. Each coordinate can look like that. And that's the general form. Right. So okay, like theta 1, 1, x, theta 1, 2, x2, theta 1, 3, x3. Because each coordinate would be a linear function. So if it's a linear function, can easily argue that each coordinate has to be a linear function as well. So each coordinate should look like that. So there's some parameters here. And 2, 1, x1 plus theta 2. This is like really linear algebra at this point. We're reviewing linear algebra. So that's a general linear function. So is there another way of writing? So each coordinate has to be like this. So it's really like that. There's 6 parameters specifying this. Is there a simpler way of writing it? So x1, x2, x3 are the same here. Coefficients are. Sorry? Oh, can you say like how should I do that?
So theta 1 transpose.
That's like theta 1. What is theta 1 transpose? So just in terms of the coordinates, I have 6 entries. So it would be a matrix times x1, x2, x3.
I was thinking to just. That's the.
Yeah, let's just expand it. How should it? Theta 1, 2. Theta 2, 1, theta 2, 2, theta 3. Okay. Okay. So now, what is a general linear function from R2 to R3 to R2 looks like? It looks like a matrix times x. Right. I'm going to call this theta times x. So going back to the question, what is a general function, linear function from x to R to the c? This matrix is 2 by 3. We extend this argument. What would something like this look like? A matrix times x, and this would be c by d. Great. So that's a general linear function from Rd to Rc. This is really linear algebra. So you can write a linear function or linear map. So you can review what linear maps are. They're defined like this. So a map is linear if, for example, this is like f theta x plus f theta y. If I add up 2 inputs, if I apply the function, it just is the sum of the 2 values. And if I, for example, scale alpha x by a number, this comes out. So this is really what it means. And a result of linear algebra says that linear maps like that from Euclidean spaces are in general like this. You can write it as a matrix times x, which we sort of proved. If you believe this, then it's like a little step to argue like that. Each coordinate has to be linear. It has to be like this form. And then you had, but that's a general linear map. And so there's this matrix theta that controls it, and that's our parameter. I'm actually going to write it for simplicity as little theta. It's a little bit confusing, but this theta is really a matrix now. It's not or maybe let's do it like capital to avoid confusion, capital theta. Okay, c by d, because that's how it translates the dimension. So x is d by 1 or d-dimensional. In Torch language, it's just dimension d. There's no 1 here, but the d-dimensional vector c by d, this is going to be a c-dimensional object. Okay. Sounds good. I'm going to plug this in here because I wanted a linear function. So that's my generalization of logistic regression. Okay. So logistic regression is a very special case because in that case, so you can see this is also a general linear map. This is like a matrix, but it's 1 by d. This is d-dimensional. So here you just need 1. The difference, there's a little bit of difference because we'll see, but that's the general form that I want. So this argument tells you that sort of roughly the generalization of logistic regression to multiple variables, like multiple classes, can be written like this, where this is the softmax function. This is going to be what, c by d, and this is d-dimensional. So the output is c-dimensional. Let me do d by 1, right? D by 1. Okay, very compact, very simple. Sounds good. This is called softmax regression or multi-logit. Has many names, or sometimes it doesn't have any name. Softmax regression or multi-logit or multinomial logistic regression. Sounds good. So it's very similar to logistic regression. It actually looks the same if you write it this way. Logistic regression is like sigma theta transpose x. This is s theta x. The difference here is that if you specialize this to c equal to 2, okay, this has to be, if I want to be careful, this has to be the y coordinate. Okay, so because the probability of y equal to 1 is this, the y coordinate, because this is like c-dimensional. If y is equal to 1, that's how you should write it. If I do it for c equal to 2, what this is saying is that the probability of y equal to 1, given x is equal to x, is let's not write it like that. For c equal to 2, the thing is, this is going to be 2-dimensional. Okay. So softmax u when c is equal to 2 would be e to the u divided by e to the u0 plus e to the u1. The other one would be e to the u1 divided by e to the u0 plus e to the u1. You can write it in terms of I can divide by e to the u, you get u1 minus u0 here. And this would be 1 minus the other one. So this is like really sigma of u1 minus u0. And here, theta transpose x, this would be 2 by d. This would be d by 1. So you really need 1 theta. This has 2 thetas. So there is a bit of over specification here. Okay. So when you write it in this way, this theta is not, so it's a little bit of redundancy. I really need 1 theta here. So this would be like theta, all right, that's theta 1 star, that's the first row, theta 2 star, that's the second row, times x. So it would be like theta 1 star x, theta 2 star x. When I apply softmax to it, it's just going to take like sigma of theta star 1 x minus theta star 2x. And then this would be 1 minus that. So this really, this I'm going to assign as a homework problem. I really did it here, but maybe not. So this really would be like the logistic regression, but with this would be like theta transpose of linear regression. So the difference of the rows of theta would be your the theta that is that corresponds to the logistic regression. So you can maybe I slide as a homework problem. If I add something, subtract from one row, add to the other, is not going to change the softmax. So there is an ambiguity when you write, because you don't need two parameters really. You really need the difference. There's really one probability that you have to specify. And when you write it as a softmax, especially in the case of fluid becomes clear, this is redundant. So you just really need this, but you're keeping two here, and you're also keeping two rows of theta. The two rows are redundant. In general, when you do softmax regression, one row is redundant. Or like there is a linear constraint, not necessarily one row, but there is redundancy in that parameter theta, which is not in logistic regression. Okay, so the redundancy means I can, let's say, subtract. You'll see, for example, that this what you can do as a homework exercise. This S is like almost invertible, but not completely. So if I add a number to each row, to each element. So you have a vector. If you add like 2 to each element, that doesn't change the output. This has some sort of normalization effect. So if I shift all the coordinates by an amount, this is not going to change anything, and that ambiguity is in theta. So if you have this theta x, and if you basically if you like subtract like something from one row, add it to the other, that has the effect of shifting all the coordinates by a constant amount, and the softmax doesn't change. And so you have to be a little bit careful, but modulo that redundancy, this is a well-defined model, and there's this correspondence with the logistic regression. Sort of clear. Okay, so I'm going to hopefully assign some problems so that you can work with this a little bit, figuring out. We're out of time, so next time I'm going to write down once you have this, it's easy to write down the log likelihood, and it would be just a generalization of the logistic regression loss. It's called cross entropy in general, and then you can minimize it using the same techniques. And that's your extension. Okay. Thank you, guys. See you next time.